Good morning, dear friends. Today we are going to discuss an important topic in coordination chemistry, that is Jahn-Teller effect. This also we call it as Jahn-Teller theorem and Jahn-Teller distortion. The famous scientists Edward Teller and Hermann Arthur Jahn were the two scientists who proposed this theorem in 1937. And this theorem has a great practical importance in understanding the chemistry of certain transition metal complexes. Okay, now according to this theorem, a non-linear system in an electronically degenerate state, distortion must occur, or that system will undergo some kind of distortion which will lower its symmetry and energy and split the degenerate state. A system which is a non-linear, we know an example for linear molecules like a carbon dioxide, it is a linear molecule. But non-linear molecules in an electronic degenerate state. That means suppose in coordination complexes, if you consider an octahedral complex, we know that the ligands octahedral, when we say octahedral means 6 ligands are approaching the central metal atom. 6 ligands are approaching the central metal atom. The 6 ligands are approaching the central metal atom along the Cartesian axis, that is x, x dash, y, y dash, z, z dash. So these are the 6 ligands approaching the central metal atom to form a coordinate covalent bond. And we know initially, which was an electronically degenerate state, d orbitals which were degenerate means having equal energy, will be raised in the presence of ligands in their energy, and as the ligand approach them completely to form a coordinate covalent bond, they lose this degeneracy and split into two levels. So octahedral, for example, it is a non-linear molecular system. Okay. Now, what is the concept of Jahn-Teller effect for this molecule? Suppose the molecules having asymmetrically distributed electrons, electron distribution which is asymmetric. For example, let us take copper complexes. For example, if you take Cu2 plus, all of us know that copper is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, copper is actually D9 4s2. But it will be taking an electronic configuration such as D10 4s2. 3D10 4s2. Okay, now it is a +2 state. +2 means it has to give up 2 electrons. So it is giving up, 3D10 4s1. So it is giving up its electron, one from the 4s orbital and one from the 3d orbitals. So it will be taking a configuration of 3d9. And we are considering it as an octahedral complex. In octahedral complex, the 9 electrons will be occupying in T2G level and EG level. So if you take, this is the T2G level having dxy, dyz, dxz, and this is EG orbital having dx square minus y square, and the Z square. The 9 electrons will be occupying Okay, these are the 9 electrons. When you take this T2G level, when you consider this T2G level, the T2G level is completely filled. The T2G level is completely filled and they are symmetrically filled. Each orbiter is having 2 electrons and all the 3 orbitals are having 2 electrons each. So they are symmetrically filled. But when you take this EG level, that is dx square minus y square and dz square, they are unsymmetrically filled because one orbital is carrying 2 electrons and another orbital is carrying 1 electron. So the unsymmetrically filled, the vacancy in the EG orbitals. There is one vacancy in the EG orbital. That vacancy we don't know. That vacancy we don't know where it is. For our easy sake we have mentioned. Now, there if the geometry is regular, if it is an octahedral geometry and if it is a regular octahedral geometry, if it is a regular octahedral geometry, the energy, regular octahedral, means the 2 EG orbitals, that is dx square minus y square and dz square both will be doubly degenerate. That means both will be having an equal amount of energy. So the filling of 2 electrons, the filling of 3 electrons, that is Eg3, can be either in dx square minus y square can have 2 electrons or dz square can have 1 electron if they are doubly degenerate. And this will be exactly equal if dz square is having 2 electron and dx square minus y square is having 1 electron. Both will be same if they are doubly degenerate. But what this Jahn-Teller effect is saying means in a non-linear molecule, when asymmetrically electrons are filled, a symmetrical electronic state is there, the degenerate electronic state will be unstable. This state will be highly unstable, and so to attain stability, this molecule as a whole will undergo some kind of distortion. The distortion will lower its symmetry and energy and it will split the degenerate state. So how this splitting can take place? Suppose there are T2G electrons here. There are 5 d orbitals of copper. In the presence of ligand, their energy is raised and again they are split into T2G and Eg. Okay, T2G and Eg. They are doubly degenerate. But this system is unsymmetrical. It will be losing its degenerate state and they also will be split into 2 levels, either dx square minus y square having 2 electrons and dz square having 1 electron, or they can be again splitting as dz square having 2 electron and dx square minus y square having 1 electron. Okay. Now, what is the possibility of the splitting? How this splitting is taking place? Now, let us consider. So, there are 2 types of configuration is possible. Suppose let us consider it is having copper complex 2Tg6 Eg3, in which dx square minus y square can have 1 electron and dz square is having 2 electrons. So now when we draw the octahedral diagram, now what happens here? All of us know that octahedral diagram means there is a central metal, that is copper in this case. Now we have different type of ligands. Suppose this is one ligands. Okay, these are x dash, y dash. Dx square minus y square means the orbitals are along the axis. So these are dx square minus y square. Simultaneously we have dz square. These are dz square orbitals. Now according to us, the filling, there is 2 electrons in the z orbital and there is only 1 electron in the dx square minus y square. Now what happens? Since there are 2 electrons, the 6 ligands are approaching along the x dash. So here you have one ligand number 2, ligand number 3, ligand number 4, ligand number 5 and ligand number 6. We are continuing the Jahn distortion. As I mentioned to you that copper 9 system we are seeing now. Copper 9 system, which has 9 electrons, will be having distribution as T2G6 and Eg3. Earlier when we have mentioned that if Eg orbitals, that is dx square minus y square dz square, are doubly degenerate, the distribution can take place either 2 ways. Okay. Now the first distribution can be T2G6 Eg3 can have an electron distribution as dx square minus y square will be having 1 electron and dz square will be having 2 electrons. Now the diagram what we are representing will be like this. Let us think that this is the central metal atom. It has 4 ligands on the xy plane, only Eg orbital. We are drawing only Eg orbital here. Okay, Eg orbital will have dx square minus y square and dz square. So along the x-axis and along the y-axis, dx square minus y square is present, and along the z-axis, dz square orbital are present. Now, as we have mentioned that dz square is having 2 electrons, I have noted 2 electrons here, and x square y square, xy plane together is having only 1 electron. Now, since it is an octahedral complex, the 6 ligands have to approach the central metal atom along the Cartesian axis, that is x dash, y dash, z dash. Now as the 6 ligands, imagine the 6 ligands are approaching the central metal atom along the Cartesian axis. Now, as the six ligands means they are electron rich species. They are electron rich species. Now, the central metal atom copper has positive charge, and around copper there are d orbitals which have an electrons. So the bonding is between the negatively charged ligand and the nucleus of the central metal atom. Now, the electron density is very high along the z-axis. The electron density is very high along the z-axis. So, the ligands again with their negative charge as they approach along the z-axis, there is a tremendous repulsion between the negative charge of the ligands and negative charge of the z orbitals. So, as a result, what happens? They are moving away from the nucleus. They go out, they are repelled with each other. The repulsion is very high, so they will be moving away from the central metal atom. They are pulled. Imagine you are pulling the z orbitals with your hand from the two directions. Now, there are four ligands which have to approach along the xy axis. There is very little electron density, so they can easily approach. But as they approach closer to each other, there is a repulsion between the balanced electrons of the central metal atom and the ligands which are approaching. So, since these z orbitals moved away from the central metal atom, the repulsion will be less, but though there is less electron density, they are coming very closer to the central metal atom. As they approach closely, there will be a repulsion between the d electrons of the central metal atom and the ligands. So, as a result, the energy, what is supposed to be T2g and Eg will be splitting into two levels again. That is, the dz square is having maximum repulsion, but the repulsion, they are moving away from each other, so they are destabilized. The distortion is, what happens is, z-axis are repelled to greater extent. They are moving away from the central metal atom. So the repulsion along the z-axis is less. But whereas these four ligands approaching along the xy axis, though there is a less electron density, but as they approach closer to the central metal atom, imagine they are approaching from all directions. So there is a higher repulsion. So the greater the repulsion, greater will be the energy. So the Eg orbital will lose their degeneracy and are split into dz square and dx square minus y square. Z orbitals are moving away from the central metal atom. So this system is called, they are having two electrons. This Z orbitals are moving away from the central metal atom because of the repulsion, but ultimately their repulsion is very minimum because they are moving away from the central metal atom. Okay, so since they are moving away from the central metal atom, it is called Z out case. Okay. Now let us think. There is a possibility in another way. Again, this T2G6 Eg3 can be distributed T2G6 Eg3 can have another possible distribution is dx square minus y square can have 2 electron and dz square can have 1 electron. Now what happens here? Again imagine we will be drawing again the same orbital diagram. Now let us consider another case, that is again copper 9 is having another way of distribution, that is Eg3 will be having dx square minus y square will be having 2 electrons and dz square will be having 1 electron. Now what happens in this system? What happens here? Okay, now when we see here the electron density, just imagine here. Okay, there is two electrons along the x square minus y square, and there is only one electron on the z axis. Now, as I mentioned to you earlier, the great repulsion will be having by these x square minus y square orbitals, because there are two electrons. Now, as the ligands are approaching the central metal atom, what happens? The repulsion will be more along the x-axis and y-axis, because already there is high electron density and ligands come with their negative charge, and there is a repulsion between these negative charge of the orbitals x square minus y square and the negative charge of the ligands. So they move away. They move away from the central metal atom because of the high repulsion. The ligands are moving away from the central metal atom. But whereas the ligands which are coming along the z-axis, since there is only one electron, there is a less electron density. But what happens? As the ligands approach closer, the repulsion will be more along the z-axis, because since z orbital is having only one electron, there is a less electron density. Ligands will approach with their electrons the central metal atom. But as they approach close to central metal atom, the metal which is having already d electrons, the repulsion will be very high. As generally when we speak, the x square minus y square only should have a maximum repulsion. But because of the repulsion, the ligands and these orbital are moving away from the central metal atom. So the repulsion will be less. Whereas the z orbital, though there is less electron density, but the ligands as they approach closer to the central metal atom, the central metal which is having already an electron density will begin to repel this z orbital. So z orbital will be having a maximum repulsion as the ligand approach. So the degenerate state orbital T2G, Eg, which they were supposed to be doubly degenerate, in this case will split as dz square and dx square minus y square. So dz square, which is lower in energy, will be having 2 electron, and dz square higher in energy will be having 1 electron. Since the z orbitals are compressed towards the central metal atom, this case is called Z in case. Okay, I will be explaining to you this once more. I know little confusion is there here. All of us know that Jahn-Teller distortion or Jahn-Teller theorem. Okay, what it says? According to the basic knowledge what we have, the crystal field is splitting in the octahedral complexes. As the ligand approach, it will be of two ways, that is T2G orbitals and EG orbital. T2G orbitals are triply generate orbitals because dxy, dyz, dxz all are in same energy. Same way, EG orbitals are doubly degenerated. Dx square minus y square, dz square is having same energy. Okay. So what happens? So far, if the electron distribution in this orbital is equal, there is no problem. There is no problem. But Jahn Teller proposed a theorem which says that if there is an unsymmetrical electronic distribution in a non-linear molecules, the electronic degenerate state will be unstable if it is an asymmetrical distribution or unsymmetrical distribution along these orbitals. The system, if it is a non-linear, it will be unstable. It will undergo some kind of distortion to lower its symmetry, to lower its energy, and as a result, the doubly degenerate, triply degenerate orbitals can be split into. That is what this theorem is proposed. Okay, to explain this theorem in more clearly, let us consider copper 2 plus complex. We know that copper is actually having 3D9, 4s2 system. Since it is a plus 2 state, means 2 electrons will be removed. 2 electrons, 1 electron from the 4s1, but it will be having an electronic configuration as copper 3D10 4s1, because we know that either completely filled or half filled orbitals are highly stable. So it will be, though general configuration is like that, it will be adjusted to like this to attain higher stability. Now, copper 2 plus means 2 electrons are removed from the central metal atom. So 1 electron from the 4s orbital and 1 electron from the 3d orbital will be removed, and it attains the configuration 3d9. 3d9 octahedral symmetry can have an electronic distribution as T2G6 and EG3. Now T2G6 is symmetrically filled. Each orbital is having 2 electrons and total 6 electrons, there is no problem. Whereas when you consider this EG level, they are unsymmetrically filled, because one orbital is only having 2 electrons and another orbital is having only 1 electron. So this unsymmetrical, it is a non-linear molecule. So like this molecule are unstable, they will undergo some kind of distortion to lower their symmetry and to lower their energy. So they will be losing their degeneracy and they will be split into 2 ways. Say, okay, if it is a regular octahedral geometry, means 2 EG orbitals will be doubly degenerate. That means they are having same energy. So EG3 is the electronic configuration here. It can have electrons either dx square minus y square can have 2 electrons and dz square 1 electron, and dz square 2 electrons and dx square minus 1 y square 1 electron. If they are doubly degenerate, that means they are having an equal, degenerate means they are having equal amount of energy, the either distribution has no problem. But what is happening here, according to Jahn-Teller theorem, this system is unstable. It will undergo some kind of a distortion. That's what the system is saying. Okay. So the first one, so this can be the distribution for the first distribution can be, okay, T2G6EG3 can have one way is dx square minus y square having 1 electron, dz square is having 2 electrons. Now what happens? You draw the diagram here. It is a regular octahedron first. Now what happens? Regular octahedron means we are drawing only EG orbital. That means x square minus y square lying along the xy axis and dz square lying along the z axis. Now what happens? Dz square is having 2 electrons. As a result, the electron density is very high along the z axis. and dx square minus y square, these four orbitals together is having only one electron. There is very less electron density. That is the basic thing. Now, the six ligands are approaching with their electronic charges to the central metal atom. The coordinate bond is between the central metal atom, or the bond is actually between the nucleus of the central metal atom and the negatively charged ligands. Now, since it is an octahedral geometry, the ligands are approaching along the x dash, y dash, z dash. I have taught all these things in the crystal field splitting for the octahedral, tetrahedral, square planar, distorted octahedral. So if you remember that, you know these ligands are approaching along the coordinate axis, that is x dash, y dash, z dash. Now what happens here? Z orbital is having two electrons. The electron density is very high on the Z orbitals. Now ligands also are approaching the Z orbitals with their negative charge. As they approach itself, these Z orbitals will say, move away. We are already having electrons. So there is a repulsion. They will be repelled away from the central metal atom. They are actually moving away from the central metal atom. They will move away from the central metal atom because of the high repulsion. Now what happens? Since it is a very less electron density along the x square minus y square, the ligands are approaching very closely, very gloriously to the central metal atom. But as they approach very closer to the central metal atom only, they realize that there are other d orbitals which are having already electrons. So what happens? They will be repelled. But they are coming very closely and they are repelled. So the repulsion will be very high along the x square and minus y square than the z square orbital, which are away from the central metal atom. So the repulsion is very high. As a result, energy also will be very high. The splitting will be d. So dz square will be having less repulsion than the x square minus y square. So dz square, the total Eg orbitals will be split into level, that is dz square, which is having less repulsion because it is moved away from the central metal atom. Dx square minus y square, which is so closer and having high repulsion, will be having maximum repulsion. Maximum repulsion increases the energy. So dx square minus y square will be having higher energy. Dz square will be having lower energy. Since z orbitals are moving away from the central metal atom, they are called z out case. This is called z out case. Okay. Now let us see what happens in the Another way of distributing electron again in this case is dx square minus y square can have two electrons and dz square can have one electron. In this case also So in this case you can see that dz square is having only one electron. Then there is very less repulsion, very less repulsion. But whereas dx square and minus square, x square minus y square is having two electrons. So their electron density is very high along the x square minus y square axis. Now imagine the ligands are approaching the central metal atom. Okay, since the electron density is very high along the x-axis and y-axis, the ligands, the repulsion is very high. Repulsion is very high and they will move away from the central metal atom. But z-axis, which is having only one electron, z-axis which is having only one electron, the repulsion is very minimum and ligands will approach closely the central metal atom. Once they approach only the central metal atom, will have another d electrons, which is that is T2g6 electrons, then it will begin to repel these z orbitals. So the repulsion coming closer to the central metal atom and phased repulsion is z orbitals. So z orbitals will be having maximum repulsion, and x square minus y square, which is though having electron density very high, but they are moving away from the central metal atom, will have less repulsion. So the maximum repulsion, maximum energy, less repulsion, minimum energy. So the orbitals which are supposed to be doubly degenerate will be splitting into two levels. The dx square minus y square, which is having a less repulsion, will be having lower energy, and dz square will be having higher energy. Now all the compounds, it is very difficult to predict which type of distribution this occurs. Whether is it taking place elongation, z out means orbitals are moved away, z orbitals, the orbitals are lying along the z axis are moved away from the central metal atom. That system is called elongation. But z in cases they are coming very closer to the central metal, they are called z compression. Most of the time z out case only is more favorable. Generally elongation of the two bonds along the z axis is energetically more favorable than elongation of four orbitals along the xy axis. And z out case is much more common than z in case. Okay. Now next topic we will see some questions and the consequences of the Jahn-Teller distortion theorem.